Yeah, it's now being recorded. Welcome, everyone. It's Tuesday, May the 9th, and I'm going to present you the second online webinar, and that's connected to the high impact weather online course. People can do it in their own time or in their office, and this is a sort of extra element in this online course, that you also have the ability to follow a lesson in convection. Well, at the moment here in the Netherlands, it's raining. It's actually quite cool. But as many of you have noticed over the last couple of weeks, there's some strong warming already going on, especially in Portugal. I saw a chat from Nuno. Nuno, hello. And also in Spain and parts of France, there is quite a strong warming. And over last weekend, we had a sort of first large-scale eruption of convection. And I'm going to show you some details in the course of this webinar, based on the theory of the ingredient-based methodology, because that's the basis of how at KNMI, but also in many NMSs in Europe, meteorologists, operational forecasters are dealing with convection. Okay, I'm going to the next slide, and yeah, I will skip this one. Oh, leren. Okay, shift this part a little bit. Yeah. So the basis of the methodology, it's called the ingredient-based methodology. What I explained in quite detail in the first webinar is shown here in the format of a so-called convection forecast scheme. And in the first webinar, I handled the first part of this convection forecast scheme, namely to look at moisture, instability, and lift, because those are the main three ingredients which are necessary for having convection. And in this webinar, I'm going to focus on the role of wind shear, and also to show you the importance of to embed wind shear in your forecasting scheme, because it has a large influence on the mode that will be chosen in the atmosphere, and that's called the convection mode. And we have more or less, roughly speaking, 4 modes, but I have to admit that in practice you always find some interchange between those 4 modes. But basically you have a single cell, a multi-cell cluster, a multi-cell squall line, and a supercell. And in the end, in this forecast scheme, I also pay some attention to the phenomena, to the hazardous weather, and especially when you look at, for instance, the convective wind gusts. There's a lot of interest in the meteorological community by improving those forecasts. And of course, you can look at a non-hydrostatic limited area model graphs. But in the end, you also have to use your mind by combining all kinds of information. Also, the real life observational information can be of added value to really issue an accurate forecast for the convective wind gust. Okay, go to the next slide. And on this slide, you can see the wind shear component. And for studying wind shear, for looking at wind shear, we normally make use of a hodograph, because that seems to be a much better and effective way to look at variations in wind direction and also wind speed with height. And what's very important is that we have to look at a term called effective shear. So it's not so easy just to look at, let's say, the difference between the wind at surface level and at 500 hectopascal, but you really have to think and to study the environment and how it looks like based on soundings, and then you can more or less determine the effective shear that is going on in the atmosphere. Okay, this is quite a simple graph which shows you the variation of wind with height. And what we normally do is that we concentrate on some certain layer. And that's mostly a layer with a thickness of 6 kilometers. And that's based on empirical research done in the United States, that when you look at that layer with that depth, then you get most of the signal out of that particular value of vertical wind shear. But why is it important? Well, in the basis, where wind shear is nothing more than a mechanism to separate the updraft from the downdraft. That's the basis of the importance of vertical wind shear. And in this photograph, you can see quite a nice image of a cumulonimbus cloud with almost no shear, because the envelope cloud is not shifted from the base of the cumulonimbus cloud. That's one of the manners to see if there is a lot of vertical wind shear in the atmosphere or not. And as you can see, the updraft will be finally killed by the downdraft. So this is a typical example again of an atmosphere with only little or less vertical wind shear, which leads to the development of a so-called single cell. But if you do have vertical wind shear, what you then see is a clear separation between the updraft and the downdraft, because the system will be a little bit more tilted, as you can see on this right photograph. Furthermore, the vertical wind shear is also important, as you can see from this image, which I lent from the COMET program, in terms of that in an atmosphere, in a sounding, in a developing cumulus or cumulonimbus cloud with a vertical variation in wind speed, a unidirectional wind shear, it's also called, you can see that there is a development of a so-called dynamical pressure perturbation. Normally, on a synoptic scale, when you look at vertical movement, then we mainly focus on hydrostatic adjustment. But in case of convection, there's a deviation from that adjustment, from that balance. And then you can see all kinds of pressure perturbations in the horizontal, but also in the vertical, which leads to much higher vertical velocities. And you can see on this image that vertical wind shear leads to, let's say, a vertical pressure perturbation with an anomaly on the left-hand side, on the windward side, a positive anomaly in pressure, and a negative anomaly on the right-hand side. And if you do not only have variation in strength, but also in direction, then you end up with a profile in which you have most of the time a varying of wind with height. That's not always the case, but most of the time it is, and also an increase in speed with height. And then you can end up with all kinds of pressure perturbations, which varies with height if you look at the axis of most of the pressure anomalies that occurs. And it plays on such a short scale that the Coriolis force is not working on it properly. So this leads to ageostrophic winds. Well, there are some typical values when you look at vertical wind shear. And based on those values, you can more or less pinpoint which kind of mode of convection will probably occur in the atmosphere. And here you can see some typical values, but it's much more important to combine in the end, the vertical wind shear amount with the amount of CAPE, what I discussed in the first webinar. Again, if we concentrate only on vertical wind shear, then you see a sort of relation based on empirical research, in which you can see the the variation of typical updraft strength, which can vary from weak all the way up to strong. Well, an effective method to look at those vertical wind shear profiles is not to look at them when you, for instance, look at the sounding and look at the variation of wind with height, but to plot them in a so-called hodograph. And a hodograph is nothing more than adding all the wind factors on an X and Y axis graph, and in the end to connect the points, the power points, the arrow points, so to speak, with each other. And then you end up with this blue graph in which you see an atmosphere in which the winds are increasing with height, but also varying with height. And in the end, that gives you a lot more detail about what kind of mode of convection you can expect. So I think that most of you, I think, are familiar with looking at those hodographs. And here you can see, for instance, that in hodograph, you can also play around with arrows like a 0 to 6 kilometer wind shear. But also, when you look at effective wind shear, that you have to leave the surface level most of the time, as I will show you in the course of this presentation. And then you have to look a little bit more up in the mid-troposphere to determine the effective amount of wind shear. So the hodograph is an important tool for showing you the vertical wind shear at a glance. And it's also important, and you need some exercises to do that, to look in a storm relative frame. So that means that you subtract the system velocity, and not only the system velocity, but also the system direction in the velocity vector. And then you end up in a so-called relative tree with respect to a storm. So for instance, if you have a storm which moves to the northeast with some certain speed, you can more or less place a red dot in the hodograph, and you can more or less then determine the wind factors relative to that point. So in this slide, you can see two things. You can see the original sounding on the upper left, and you can see, based on this sounding and also based on the estimated winds, because this is a model sounding, you can plot them on a hodograph, and you can connect the points, and that leads you to a so-called hodograph, in which you can look at not only at the variation in strength, but also at the form of the graph, which tells you a lot more about the variation in direction. And well, it's in practice, it's more effective to look at the shear values, which are really important in the layer where the cumulonimbus clouds are developing, and that's not always exactly from the ground. So in this sounding, you can see quite a nice inversion around 900 hectopascal. So that means that for embed to incorporate the vertical wind shear, you need to start at 900 hectopascal, for instance, and then go up in the mid-troposphere all the way up 6 kilometers from that starting point to have a more sensible, more effective way of looking at wind shear. As you can see here, you end up in the purple line between the blue line and the purple line, and that tells you the amount of effective vertical wind shear. Well, in the end, you have to look at your convective forecasting scheme and to think about which mode of convection is most likely to occur. Well, then you can see based on this image that for a single cell, that's quite logical. You do not have vertical wind shear at all. So that's the typical holograph with a very slight variation. But if you look at, for instance, the multicell cluster, but also the multicell squalline, then you see that there is some kind of strength variation, not direction variation, but typical strength variation. And for a multicell cluster, you can see that the variation in speed is quite limited. And for a squalline, you can see a large variation in wind speed. And for the supercell, that's the highest mode of convection. You do not only see a vertical wind shear in speed, but also in direction. And that's the most effective, that's the most organized way convection can have in the Earth's atmosphere. So this is sort of summary that you can divide the types of organization in a poor segment, moderate segment, and a good segment. And it all depends on, well, vertical wind shear, but in the end also you have to take the amount of cape into consideration to have a sort of final clue about which type of convection is most probable. And therefore you need this diagram, because on this diagram you can see on the y-axis the effective wind shear in knots, and on the x-axis, on the horizontal axis, you can see the cape values. And well, in the course of this presentation, I will show you one of the first major eruptions that took place over the weekend in Europe. And I also show you the Estofax forecast that was done quite nicely by the ESSL team. And I guess that most of you are familiar with those types of forecasts. It was 10, 15 years ago, it was quite new. But now it's quite common, I think, for most of you to have a look at those forecasts, because they make use of the ingredient-based methodologies. So they really go through that diagram, and they really go through all the steps when they look at, and then they look at moisture, at instability, and at lift, and they also incorporate values of effective vertical wind shear. But I will come to that later on. Well, if we concentrate on this slide, then you can see that the single cell, you can find it in the lower left side of this diagram, of course, because you can see a less effective wind shear and also a small amount of cape. But at the same time, maybe that surprised you. You can see if you go upwards from a single cell and you end up in the upper left side of this diagram, then you see a term called mini supercell. Well, actually, I do not like terms like mini, because I know that the media likes to use mini or maxi, but in reality, in meteorology, it's not really that a mini supercell has many consequences. So, what I mean with that is that you can have a supercell mode with a lot of wind shear but less cape. And in practice, that means that you have supercells with a limited extent in the vertical. So not all the way up to the tropopause, but mainly confined to the lowest 4 or 5 kilometers. But if you look at summertime convection, you merely focus on a combination of high cape values and high effective wind shear values. And then you can see in the middle part of the diagram that, let's say, for Cape values between 500 and 1000, or between 500 and 1500 joule per kilogram, and let's say 30 or 40 knots as effective vertical wind shear, then you end up with really, good organized convection. And well, multicell or squall lines are quite common over the European continent in summertime. And well, it's very important as an operational forecaster that you have a clue beforehand which type of convection will probably occur in the course of the day, or sometimes also during night. And our experience is that Cape is of course important, but it is indicative, and that means that the wind shear is often more important than the Cape itself. And to give you an example, in wintertime convection, you do not have much Cape. It's more or less limited between 0 and 500 joule per kilogram. But then you can end up, well, not always with mini supercells, but you can easily end up with multicell or quite strong squall lines, wintertime squall lines. So that's very important to stress that out, that in the end, the vertical wind shear is more or less leading. Well, to start with, to showing you a few more detailed and worked out examples of those modes of convection. I think that can be very interesting. And then soon I will go over to the actual example that happened last Saturday over Western Europe. Well, this is, I think, quite easy to understand, because this is an example of the single cell convection, in which you can see less vertical wind shear, so the updraft will be influenced by the downdraft, and that means that the single cell has a quite short duration of time, as you can see in this slide. So most of the time that a single cell will live for about half an hour, or at least an hour. And what is also very important, there is no or less interaction with other cells. And there is, in the end, a low risk of hazardous weather. And this is an example from a single cell that was photographed over the eastern part of the Netherlands, looking into Germany. And you can see on the radar image, I play it again, you can see some echoes on the radar screen, on the radar loop, in which you can see the development of one echo, and half an hour later that echo will die out. So this is the typical sounding connected to a single cell. You can see quite a moist layer in which convection is possible from the ground with some warming. And well, you can see less variation in wind. Only the last part in the photograph, that's the purple line between 8 and 11 kilometers, you can see some signal of an increase of wind. But if you look at the effective wind shear again, then you have to look at the layer between, for this sounding, between the surface and 6 kilometer height, and then you end up with almost no variation. Well, if you, for instance, in the diagram, look at less wind shear but a lot of Cape, then you end up with so-called toll storms. So those are visible in terms of a very strong ascent motion due to convection, due to very strong thermals, in a very unstable atmosphere, but only little wind shear. So that again means that the updraft will be finally killed by the downdraft after some short while. But the pulse storm is especially important because of that large amount of Cape there will be some more hazardous weather signals, like a large amount of rain, which can lead to flooding, but also the development of hail, lightning, and even the development of quite a strong downburst. And this is an example that took place in the Netherlands. You can see some very strong echoes for a very short time. So it developed, and then an hour later, it diminishes, as you can see on this radar loop. And because of a very little wind shear, you can see the photograph on the right-hand side with the typical anvil on top of the base of the cumulonimbus cloud. That's also a sign of very little wind shear. And you can see the atmosphere, you can see the sounding, which is quite unstable, and which allowed convection all the way up from the ground. So there's no inversion in between. But at the same time, you can see less or no vertical wind shear. And that leads to this type of hodograph with the diverse dots quite close to each other. Well, here you can see the 3 stages of a pill storm. You can see the growing stage at 2 o'clock in the afternoon, and then 15 minutes later, you can see with a pill storm the major stage, and that led in the Netherlands to large hail and very heavy precipitation, also downburst. And then half an hour later, it was already the dissipating stage. So that's a typical example of a pill storm, and that can lead to a lot of hazardous weather, as you can see on those 2 photographs. In summary, if you look at a single cell in a pill storm, then you can see that both modes of convections do have a very low value of shear, but the pill storm that differs from the single cell in terms of very high Cape values, of a lot higher Cape values, so to speak. Now I go over to a much more interesting mode, which is, I think, for most of the forecasters, also a very difficult type of convection, and that's a multicell. And in multicell, you have a mode of convection in which there is a separation between the updraft and the downdraft, and that leads to a longer lifetime, but it also leads to interaction with other cells. And that can lead to, a much longer time window for a larger area in which you have to deal with hazardous weather, which can lead to flooding, hail, lightning, and also the downburst. And this is a typical image you can find in a lot of textbooks and on the internet of a cross-section of a multicell cluster. And it's typical the mother cell and the daughter cells, which shows you the sequence of a repeating convection that will take place when the outflow of the first cell will trigger a new updraft. And again, after a while, that new updraft will develop a new downdraft, and that will trigger a new updraft besides it. So you end up with a sequence of all kinds of cells, and you can more or less see this photograph, the different updrafts next to each other, as a sort of result of outflow that triggers new convection in some certain direction. And here you can see other photograph of some certain anvil, a few anvil clouds. And this is a radar loop in which you can find a typical radar images that belongs to multicell clusters. And how do you recognize this? When you look at especially the the sequence of the black colors and the deep red colors, you more or less, when you study it carefully, you can see a sort of repetition, that besides those echoes, you can see the development of new echoes. And for that, of course, you need vertical wind shear. And I hope that I can show you on this sounding, based on this sounding, that this is really an atmosphere with a lot of vertical wind shear. And on this sounding, you can also see that there is quite a strong inversion between 500 and 600 hectopascal. But overall, there is convection possible between ground level and 500, 600 hectopascal. And in between, in that layer, you can see that you end up with a lot of vertical wind shear. Even that vertical wind shear will be something like 80 or 90 knots. So that's a lot of vertical wind shear. And also for the multi-cell clusters, you can look at the different stages, as you can see here. So you do have individual cells, you have clustering cells, and you have multi-cell complex, and that's all based on the theory of multi-cell cluster triggering, where you do need some certain amount of K, but also vertical wind shear. Here you can see some nice images of the flooding and the hailstones. And here you can see a summary in this table, where you can see the effective K values, the effective shear values. You do not have to take that literally, so that's maybe it's not so sensible to show you in so much detail those numbers, because it can differ a little bit, but it's roughly speaking a sort of first estimate. You have to look at that in such a way. But then another type of multi-cell cluster is a solution in the atmosphere where you can find a sort of strong line convection, where the different updrafts and downdrafts are again shifted because of the vertical wind shear, but because of their movement, that there is a sort of netto line of convection, and that can persist for several hours, and that forms a sort of aligned gust front. So they work together, all those cells, and then you end up with a so-called squall line. And the squall line can be quite dangerous in the sense that it has a large influence in terms of hazardous weather phenomena, and also the long duration. That means that quite a large area can be affected by that type of weather phenomena. Here you can see quite a famous loop in which a squall line entered the Netherlands from Belgium. You can see that it developed over the border between France and Belgium, and then moved into the Netherlands. And if you look carefully, then you can also see a sort of isolated cell over Antwerpen-Ghent in the beginning of the loop, and that was a mode of convection with supercell characteristics. But the line itself is clearly a squall line, and that moved into the Netherlands with an enormous amount of impact, an enormous amount of lightning, a large hail, and even a lot of damage in the city areas of The Hague, Rotterdam, but also Schiphol Airport was hit quite severely by this squall line. And look at the time; it was in the middle of the night. So, well, I will show you the sounding in a minute. But those squall lines, when you look during daylight at a squall line, you can more or less see, for instance, this kind of images. You can see the line segment in it, and you can see a sort of rolling cloud on the foreside. And that's merely a sign of the forefront of an outflow, quite a strong outflow boundary. Here you can see other nice images, and this is the sounding based on that nighttime convection that took place. And because it was nighttime, you do have a sort of ground inversion. So that means that the convection started not from the ground, but it started a little bit more above the ground, somewhere around 900 or 925 hectopascal. And then all the way up, it was the convection was able to grow all the way up to the tropopause. And these are some plots of the highest wind gust, not in knots, but in meters per second. So that means for the Amsterdam region, they experienced during the night wind gusts all the way up to 60 knots. So yeah, and in between, because yeah, we have a quite coarse, dense meso network, but in between with convective wind gust, you always end up with higher values, as most of you probably know. So you have to be lucky if a convective wind gust will be measured by your weather station. Okay, here you can see another few examples. The right image, that's an image from the loop I just showed you, and the left radar image is another example of a of a squall line, and it differs a bit because on the right hand side you can see a small bow segment in the middle part of the squall line, while in the left image you do not see the bow segment, so it differs a bit. Well, here you can see again the loop on the right hand side, and on the left hand side you can see a sort of detailed a radar image of a squall line with a quite nicely developed bow echo. And this was quite a nasty situation where people in the Netherlands died. 2 people died because of the extremely severe wind gust that came out of this bow echo segment. And for the second time in Dutch history, 5 electricity masts were blown down, and the estimated wind speeds were around 200 kilometers per hour. 200 kilometers per hour, and it can only develop those high wind gusts when when a bow echo is able to develop in a squall line. And how does it work? Well, it's a little bit complicated, but it depends a little bit on the dynamical structure of a squall line. Here you can see a cross section, and you can see the amount of precipitation in the light gray and dark gray area in the left image, and you can see a rear inflow jet, and you see a front to rear flow. But we have to focus especially on the rear inflow jet. That's a sort of extra jet, which tends to increase the wind with, let's say, 15, 20 or 25 knots on an altitude of typically 1 or 1.5 kilometer high. And when that rear inflow jet comes to the ground, then a bow echo can form, because it's a sort of jet that pushes that part of the squall line a little bit more forward in comparison with the other parts of the squall line. So you end up with a bow echo, in which you can see on the right image from above. So that's not a vertical cross section, but you look on the right image from above, and then you can see the developing rear inflow jet, which leads to a bow echo. And well, if you look at the time scale, such a squall line with bow segment can survive for several hours. So that means that the Coriolis force can have its influence. And one of the signs is that it ends up as a sort of comma echo. So that means that on both sides, due to horizontal wind shear, that's different from vertical wind shear, I have to say. You have some spiral motion. You have the development of vortices, and especially the most northern vortex, the Coriolis force will work together to make it quite a clear, vortex, cyclonic vortex. So that's also a sign that because of the long duration, that the Coriolis force will have its influence. Well, if you look at bow echoes in more detail, then sometimes you can find on the northern edge some mesovortex, which can be quite damaging for the in terms of an extra amount of wind speed. So you do not only have the translation part of the descending rear inflow yet, but also the rotational part. So that adds up. So that means that sometimes in the landscape you can see, by looking at falling trees, that there is some spiral pattern. And you do not always need a tornado to have that, but also a mesovortex on the forefront of a bow echo can also cause this type of damage. Well, another very important rule of thumb, which we always use at KNMI during the convection days in the summer, especially in summertime, is that you determine when you think a squall line will form, that you determine two things. That's the line of forcing, the orientation of the lining forcing, in comparison with the storm factor, so to speak. So the storm factor is nothing more than the factor that determines the direction and speed where the squall line is moving to. And what is very important is that the movement of the shower, of the storm, when it has an angle of 90 degrees with the line forcing, then you have most of the squall line formation, while when the storm is moving parallel to the line forcing, you end up with most of the time only some clustered convection, which is less dangerous than the left example, when you do have an angle of 90 degrees. So that's a squall line. That's most of the time when you do not have a supercell, that the squall line is the most upper part of the organization that is possible. This is an example of last Saturday, because as I told you, we experienced quite a lot of warming, especially over the southwestern part of Europe, and in combination with quite an active jet stream, you more or less have the first eruption of convection on a large scale, typically in the last week of April or the first week of May. That's a sort of sequence that you can encounter almost each year. And so it's more or less the starting point of the convection season. And on this map, which I made in the ePort JavaScript environment of EUMETCAL, you can see in blue the 500 hectopascal geopotential height. You can see an air mass image on the background, and this is the image of last Saturday at 12 UTC. And in red you can see the theta E values at 850 hectopascal. And the reason why I show you this image, this graph, is that that you can have a clue by looking at you can have a clue of the risk for the development of convection just by looking at moisture and lift. You cannot look at instability. You need a little bit more than that. But if I start by looking at lift mechanism, then you see that over the Gulf of Biscay, you can see an upper level trough. And you can see a upper level high or a ridge over northern France, well, all the way up from the northern North Sea via northern France, east of Paris, into the western Mediterranean Sea. And the trough again is over the Gulf of Biscay, and then quite sharply over Portugal, and all the way up down to the south part of Portugal. And between the trough and the ridge, you do have most of the ascent motion because of the synoptic scale ascent motion produced by, for instance, positive vorticity advection. And if you take a look at the theta E values, then you more or less can see a sort of tongue of higher theta E values at 850 or 900 hectopascal, all the way ranging from the Iberian Peninsula via France into southern part of England. And especially that combination is typical for leading to eruption of convection of quite a large area. And here you can see especially the southern part of France for 3 hours later for 15 UTC. You can see the proc sounding with the corresponding hodograph on the upper left side. And you can see also on the large image, you can see the cross that's somewhere near, I think, near Toulouse in the south of France. You can see the point where the model sounding was based on, was calculated. And well, you can see on the sounding itself that convection from the ground is possible. You also can see quite a lot of vertical wind shear, and that's quite logical because there is quite a yet over that part of Europe. And from the hodograph, you can see more or less unidirectional wind shear. I hope you can see that. That is quite nicely unidirectional wind shear. Well, 6 hours later, at 18 UTC, I hope you can see the difference between 12 UTC. You can see that the upper level trough has shifted a little bit more to the east, and that you can see the eruption of quite a heavy convection in this air mass image over the central part of France. Here you can see the radar image, and you can see some multi-clusters and even some clusters if you zoom in with some supercell characteristics. And Estofex produced, when there is convection going on a daily base, forecast, as most of you probably know, and they issued a warning level 2 for the middle and southern parts of France. And I have added up also the observations in terms of hazardous weather, and you can see from the green triangles that there was a lot of hail observations that was done in that area of level 2. Okay, I'm looking at the time. Yeah. Okay, in the next few slides, I'm going to show you some typical synoptic situations which are so typical for the European, especially the Western European continent. And that's divided into convection in the warm sector and the Spanish plume. That's convection on the relative high pressure. That's also possible. But I do not have time for that, but I will ask you when you have this presentation, I will arrange it via Tomislav that you can have this presentation, that you can also look up a nice example of convection in the winter time. And I know that Veronica is also in the house. I saw Veronica coming in 1 hour ago. She also did a lot of work on the conceptual models in the past and about all kinds of phenomena. So and that's still visible in the SAT manual. Well, this is also an example of the convection that took place over France last Saturday, namely that we had quite nicely a warm sector, and that in that warm sector convection can take place. And more or less, when you look at the upper level pattern, that's quite logical. You have a ridge over the continent and a trough over the Gulf of Biscay or Iberian Peninsula. And then you can see an approaching cold front, and most of the time also a thermal low over France. But what is a lot more important is when you look at a little bit more detail about the dynamical component of the development of convection, because you need a little bit more information to determine how much and what the risk is for convection in such a case. Because when you look in the warm sector, most of the time influenced by that ridge of high pressure, the convection can be suppressed by the descending motion under that ridge of high pressure. But if you move a little bit more into the direction of the cold front, along the western side of that ridge, so to speak, then you have a much higher risk for the development of convection. Well, on this image, satellite image, you can see in green a so-called thickness value, which tells you a little bit more about the energy or the temperature of the layer in the lowest couple of kilometers in the troposphere. And at the same time, you can see in blue, that's called that's a parameter that tells you a little bit more about where you can find a frontal system, in this situation a cold front. And the maximum value refers to the most probable position of the cold front from England over western France into Spain. And especially on the eastern side, you can see an ideal combination of warm air, which is most of the time also moist air, some ascending motion, and at the same time an approaching cold front, which also can incorporate some extra lift. So you can look at a variety of all kinds of parameters by estimating the risk for convection. So again, you can look at theta E values, which gives you a clue about the latent energy, which is available especially in the low part of the atmosphere, because we are looking at 850 hectopascal. So that's quite a logical level in the atmosphere for looking at potential temperature levels, because it's not so influenced by diurnal variation, and so you can merely look at that level. And in this example, and on this satellite image, you can already see the eruption of convection over France, and at the same time a so-called tongue of maximum theta E values, which is so characteristic for areas of convection in the warm sector. Well, here you can see some more detail, but because of the time, I will a little bit go through a few more slides, and then I will leave the room for you for questions. Because the rest of this presentation you can easily look up yourself with quite some nice examples. But to end up this webinar, I will show you a little bit more information about that warm sector. And what is especially important in the warm sector is that you look at a range of dynamical forcings. And it can be a front, what I just mentioned. But what can also be important are on the mesoscale, for instance, the outflow boundaries. And the outflow boundaries you have to look into much more detail when convection is going on. For instance, to radar images, also satellite images, but especially radar images nowadays. The Doppler radar images give you signs for where you can find outflow boundaries, and also to look at your ground observations to find out where you can have signs for an outflow boundaries. Which is also very important is the low level yet and the orography. Well, if you look at over flat country, then you can most of the time skip the orography, and where you are far away from the sea, also sea breeze front. And also very important are the upper level dynamic forcings, like the trough I just mentioned, but also jet streaks with the 4 quadrants are very important, and the potential vorticity anomaly, which you can especially find just on the cold side, on the polar side of a jet streak, and that can also, enhances the amount of real vorticity, which leads via positive vorticity attraction to some extra ascent motion, and that is most of the time in summertime when you have a strong temperature gradient between the continent and the much cooler sea is going on. So that has also an important extra influence on the ascent motion along a cold front. I think when I look at the time that I handled most of the information for today. So now I will go over to you for asking some questions, and you can also ask your questions by using the chat. So please do so. Then we have time for some interaction. Okay.
Thanks for the explanation. It was quite in-depth. And I think we have the first question from Vlad, so you can unmute yourself. Yeah.
Hello, Rob, once again. Thank you very much for this nice presentation. My question will be, is let's say, a technical one, if I may ask. You had a slide, if I remember well, you had a slide where we could see a SQT diagram, if I remember well.
Yeah.
Could you please tell me if that resource is freely on which website we can access it? Or this is from the KNMI and it's not available for the public?
Yeah, that's always a little bit of a problem. That's a typical diagram we use at KNMI. I have to admit that, and so it's I know that there is on the internet a website where you can find both formats. So I have to look it up for you, and then I will send it to. I think I will send it to Thomas Love so that he can share it with all of you. So I will look it up for you.
Thank you very much. Thank you very much. And if I may ask another question, from your experience, also as an aeronautical forecaster, would you mind telling me if you have ever seen some, let's say, some a slight or a bigger decrease in visibility during pulsating thunderstorms on the approach area with regard to heavy rainfall, or you didn't have any reports on this?
Do you mean that for the landing or
exactly the final landing stage?
Yeah, we at Amsterdam Airport, but also Rotterdam, Eelde and Beek, and also Lelystad. Those are the major airports in the Netherlands. We do have camera footage, and we have access to that real time 24 hours a day in our forecast office. And sometimes, especially during daytime, of course, we literally can see the decrease in horizontal visibility. Is that what you mean? Because, yeah.
Exactly. And if you also have these cameras, because we also in Romania have this system, but unfortunately we don't have measuring systems. I mean, we can only observe changes with the camera, but we don't have LiDAR system now installed in order to measure exactly the decrease in visibility.
Yeah, and now I know what you mean. Yeah. Well, we do have LiDAR at Schiphol International Airport, Amsterdam Airport, in combination with quite a dense network of visibility measurements, or in combination with camera. So I can imagine that we do have an archive in which we can look up some specific situations where in the approach a very distinct decrease in visibility took place. Yeah.
Thank you very much, Rob. Thank you very much once again.
Yeah. I can see some questions from the chat. Let me start with the first question asked by Ina. I have a concern about the terms line squall and squall line. Line squall is a belt of zone of intense thunderstorms spanning 100 to 300 kilometers roughly, orientated north-south in length. This means that line squall comprises a lot of lined up. Yeah. Yeah. Now, he's asking me a question about the term line squall and squall line. And I have to say that in the Netherlands at KNMI, we only use the term squall line. So I'm not familiar with the term line squall, but I can imagine that maybe in other countries, they do use that word, line squall. So I think it's I have to think about that. Sorry, that's a little bit of a surprise, but I will copy this chat in the end. So maybe I will come back to that. And then a question. From Andreas. In the case that I observed last summer, shear prevented CBs to develop. Is there a relation or a rule of thumb that sets cape and shear in relation to see when shear is too strong and convection will be blown away? Yeah, that's a very good question, Andreas. I did not embed this part into my presentation, but you are right that sometimes shear will, in the end, a limitation for the CBs to develop, and it depends on a sort of balance you need, and that balance that depends on the amount of convection, the amount of vertical motion, the spatial extent of vertical motion. That is very important, because when you only have vertical motion confined to a small area, then what merely happens is that the vertical shear will shift the upper part from the lower part of the developing towering cumulus, whereby the towering cumulus cannot develop further. And so I think it's more a way of looking at the spatial extent of the convection that is starting to develop, that determines if convection is able to further grow. Yeah. Is there a simple relation, linear or not, between CAPE and SYN? Will deep convection occur or not? That's from Branko. Thank you for your question, Branko. There is, you will also, you will always have to look at the combination of CAPE and SYN. And with deep convection, you most of the time have SYN in the first place in the beginning. So you need a lot of energy that you have to put into the boundary layer before the SYN can be overcome. And then that means that you end up with a lot of deep convection in the end. And there's not a simple relation. You have to look at every type of convection again by looking at your profiles, of course. Also the other factors like the environment itself in the horizontal, how much moisture is available, how much trigger zones, how much forcing mechanisms will be in place, etc., etc. And that in the end depends the chance that deep convection can occur.
There is, sorry for interrupting. There are two questions. Nulu has raised a hand, and there is a question from Sardar in the chat. If you scroll up a bit, I can post it again.
Yes, please.
So this is from Sardar. So.
Oh yeah. What are the criteria during thunderstorms for suspending airport operation? Or is there any limitation for airport operation during thunderstorms? The answer is that it depends on the type of airport operation. It depends on the size of the plane itself. What type of criteria will be used. But in general, when you look at deep convection, there is a sort of general rule of thumb that planes are not allowed to take off or to land or to fly through a complex of deep convection. That's a rule of thumb. But if the convection is less developed, then it depends on the size of the plane, which type of criteria will be used. That's, I think, the answer based on my experience for the Schiphol and Rotterdam airport region.
Do you want to ask your question?
Yep.
Okay. Hello, Rob.
Hi.
First of all, thank you very much for this excellent summary on the convection modes and the view on the shear factor. When I was just wanting to make a comment question, when you were presenting the bow echo and the meso vortices, and you showed us a slide where you have the squall line versus the direction of the movement of the squall line. I don't know if you remember this slide. Yeah. And you had these two possibilities. Of course, you mentioned that the most damaging one was the one with the direction in a perpendicular line to the squall line, right?
Yeah. Yeah.
In terms of, you are thinking about, of course, the wind impact, right? The impact in terms of wind in the surface.
Yeah.
Yeah. The thing is that, just a comment is that when you were mentioning, I was having in the back of my mind the most recent case for squall line in Portugal that we had, which was in December, but it was related to a precipitation one. And when you were mentioning the perpendicular being more trouble, I was thinking that in our case, for the precipitation, it was the opposite, because it was when you had the squall line parallel with the direction of movement, of course. Yeah. And so, of course, you're thinking about the wind, right? So, yeah. And I was in the back of my mind thinking about our recent case with the precipitation, and I think, oh, but that's in our case for the precipitation, it was not like that. I was just wanting to share with you.
Yeah.
Because we had a very severe case of flooding in Lisbon in December, in the beginning of December. And in fact, because there was no problem on the winds in that case. In fact, it was really a very heavy amount of precipitation, and the squall line just formed over Lisbon. It was a very tough one, and then it moved parallel to the axis. And then the precipitation was an issue.
Yeah, I think this is a very nice example of a case, as you mentioned, that you have a parallel movement to your line of forcing, so to speak, and then you can end up also with a situation where you can have quite a strong downdraft with a lot of damaging winds. And for people who followed my first webinar, I paid some attention to the different contributions that leads to a convective wind gust. That's a precipitation, where Nuno is referring to. That's a very important one. That's the entrainment with drier air. That's a limited factor of it can be of a limited factor. But also the melting of precipitation, and then the precipitation itself. That is, of course, a positive effect on the strength of convective downdraft. And you also have the vertical exchange of upper level winds all the way downwards to the ground. That's also a factor that you have to take into account. And then as a fourth factor, you do have that that orientation angle between the movement of the storm and the line of forcing. The orientation of the line of forcing, so to speak, and that's what I'm trying to say is that you have to look at all the different contributions to determine if a storm is capable of producing high damaging winds. And again, for that part I discussed in this webinar, the orientation angle is especially important for the total movement and the speed of the squall line itself. So that's I think the most important result that will come out of that orientation. Yeah.
Okay, thanks.
I think Claude has a follow-up question, so go ahead.
Yeah, just a little comment on what you said, Rob. I was thinking about the last question regarding thunderstorm and suspending airport operation. From my experience as a former military and civil aviation pilot, with regard to my experience as an aviation meteorologist, I would say that the right of suspending airport operations stays with the meteorologist from the airport, but for example, for continuing the approach or trying to land in a storm, for example, this responsibility stays with the pilot. And why I'm saying this is that many modern airlines, almost all of them, if not all of them, have onboard weather radars, and they can and the pilots can see exactly what kind of reflectivity, I mean the degree of reflectivity they can measure. Of course, that's not a very, let's say, modern and very expensive equipment, so it's quite basic quite basic as an equipment, but I would say that the pilot has the responsibility to see exactly. For example, during my experience as a civil pilot, when we had reflectivities of over 40, 45 maximum, we had to discontinue the approach, for example. And during my military career, we had the maximum of 50, 55.
And with 55, you mean the flight level height of the CBs?
No, the reflectivity.
Oh, sorry, the DBZ. Yeah, okay.
Yeah, exactly, exactly.
Yeah, yeah. For the Amsterdam region, we have quite a close contact with the air traffic control center, and I know also from your story that the pilots itself, they do have access to onboard radar, so they can have their own accurate information. But in the end, when there is really deep convection and there is a risk for quite a strong downburst, then the air traffic control center can overrule the decision made by the pilots. And that's because of, when I look at Portugal in the early 90s, there was a very large accident at Faro Airport because an airplane crashes on the ground because of a strong downburst that was not visible on the onboard radar. Because on the onboard radar in those times, they were only able to look at precip on a very coarse scale. But nowadays, we do have a lot more information on vertical wind shear and also horizontal wind shear, which gives the air traffic control center the opportunity to make a sort of final decision for even closing their airport for some time. But if you do have just normal convection, which is not too extreme, then the pilot itself can make a decision. Yeah, I agree with you. Yeah.
One last question that I can see is from Sardar. He is asking if there is any open source for the soundings and SQT and convection parameters.
Yes, there is an open source. I have to. I can collect all that information and send it to you, Tomislav.
Yes.
There is even an open source for making your own soundings based on ECMWF data for the very short term, for the next 24 hours, on the EUMETCAL website, on the ePort Pro. That's a little bit different from ePort Java, but ePort Pro gives you the ability to make your own model or proc sounding. So that's not a measured sounding, but it's a calculated sounding based on ECMWF data. And that's, I think, a very strong tool, which most of the NMSs in Europe are going to make use of in the next couple of years. At KNMI, we do make use of it, and that's a very strong methodology that you can point everywhere you like on the planet. If you look at ECMWF data, of course, it's a global model. But for the limited area models, you're nowadays also able to make a proc sounding for every part of your own country. So I think that's very interesting for the very short term when you have to make a forecast on a day where convection can occur. And Tomislav is making a sort of follow-up mail with this material, so I will send it afterwards, today or probably tomorrow. I will collect that information. I will send it to Tomislav.
I think that's all the questions that we have.
Yeah.
Quite a long Q&A. So yeah, thanks for the webinar. I'm going to stop the recording.